Hey guys, welcome to our machine learning final project demo by me, Asif, and Nick. Our team project name was Datasphere. Our first dataset was the S&P 500 stock dataset, and we were performing a regression task with Lasso and ElasticNet models, and this was our time series dataset. We had three datasets that we were working with for this. We had the S&P 500, the actual index, and then the stock CSV. The company CSV contained various metadata like stock symbol, sector, city, weight, as we can see here. And then for our index dataset, we had two columns, which was just the day and then the actual values of the S&P 500. No missing values, so it was a pretty clean data. And then here's a visualization of the S&P 500 over time. And then for our stocks data set, we had a lot of data here. It was almost 1.9 million rows and then 8 columns. And we had a range of 2010 to 2024. As for pre-processing, we just removed some NA values from our stock data because we had a lot. We one hot encoded the category variables, and our index data set was already pretty clean. And then for feature engineering, we removed unwanted features like business summary and short name that were useless, and then we created some of our own, such as rolling returns and 1 month lag, 2 month lag. Now, actual processing on the data set, we had to make sure that all the data set is prepared, create the 80-20 split in the data for training and test data, and then use time series cross-validation because we have time series data, and then tune our model parameters. At the bottom right, you can see we have 47,000 training samples and almost 12,000 testing samples. And then actual processing on the data set, here we're importing our models, the last one, ElasticNet models from scikit-learn. We standardize our data set by calling the scalar transformation, which is x minus the mean divided by standard deviation. And then we have our time series split right here by setting it to 5 to get our cross-validation. And then here we are setting up our parameters for the lasso model. So alpha is going to help us choose our parameter for the L1 regularization. And then we have our time series cross-validation, our maximum iterations that we want to do until we converge, which is 5,000 at the max. Our tolerance is how tolerant we are in terms of converging. So if the lower the number, the more precise, but it takes longer to converge. Number of jobs is how many cores I want to use on my actual laptop, so -1 means max. And then random state 42 ensures that we have the same results every single time. So in this graph in the middle, you can see that our best alpha and our lowest mean squared error was at a value of 0.00486, and our R-squared score was 0.0375. And then for our actual ElasticNet model, we had the L1 ratio, which is a combination of L1 and L2 regularization. So it should give us slightly better performance, which is exactly what it did. But as you can see, in terms of feature importance, Lasso and ElasticNet performed very, very similar. And our L1 ratio was 0.1, the best one, and our best alpha was 0.0047, but our R-squared score was still ended up being the same. For the metrics, we improved a little bit in the MSE with a 4.4 reduction in prediction error. But as you can see on the right, for every single folder, both the models are very, very close. Now here we actually perform the processing on our test data, but now we use the values that we already calculated. So the alpha that was optimal, and then the alpha and then the L1 ratio that was optimal from the slides before. And then here's our actual results. As you can see, we did a very bad job, unfortunately. We were highly overfit to the training data, and it was very hard to predict the unpredictable nature of a stock market. So here we'll see we're good at predicting values that are like close to like within the 2% monthly range, but outside of that, we're not good at predicting any extreme values. And so yeah, we were both very overfit to the training data. And we slightly improved our MSE, but not enough for it to be meaningful. Training time, it took almost 2 minutes for the ElasticNet model. The Lasso training time was 8.73 seconds. ElasticNet used one more feature than Lasso, and then both were very similar in terms of stability. And here are their top features.
Hi, I'm Nick, and I'll be going over our brain tumor MRI dataset, which is our imaging dataset where we performed a classification task with the SVM and random forest. So dataset exploration, we used OpenCV to analyze the images, and here's our training and testing count breakdown, as well as the sample class images and the pixel intensity distributions. For pre-processing, we began by normalizing the pixel values, dividing by 255, and also one-hot encoding the 4 classes. As you can see here on the right, we include the 4 classes of glioma, meningioma, no tumor, and pituitary. For feature engineering, we used principal component analysis, or PCA. Since there are 128 by 128 pixels for each image, we reduced through PCA to 1600 components while preserving most of the variance at 97%. And for processing, we use hyperparameter optimization with grid search CV to tune C and gamma for an SVM with an RBF kernel using 3-fold cross-validation. And it's also very efficient since we leverage all the CPU cores to speed up the grid search process. For these results, we consistently see high averages across the board with lower values for glioma and meningioma. Very good results overall with over 96% accuracy. For the random forest, we again use grid search CV for optimization to improve the random forest performance and also train efficiently. with parallel processing for faster execution as we train the model. Our results here were a bit worse, but still decent at about 88%, and we can see significantly lower values for glioma and meningioma, with slightly lower values for pituitary. And here, this is essentially an 80-20 train test split using the given train and test files. As shown in the confusion matrices for SVM, there's slightly more misclassifications for glioma and meningioma, whereas random forest has more for those same classes and slightly less for pituitary. Here we can see the top 10 features obtained through random forest, with PC2 and PC1 having by far the greatest effect in classification. And for our comparison, we can see that SVM outperforms random forest across all metrics, and for computational complexity, SVM is faster for a medium-sized dataset like ours, so therefore we recommend SVM. Now we'll go ahead with our dataset 3, energy consumption, which is our tabular dataset where we perform a clustering task with k-means and k-medians. So for our dataset exploration, we use several validation functions as well as missing value analysis, and also find our categorical variables while representing some summary statistics and histograms, which are not depicted here but included within our notebook. Furthermore, here we can see that some countries like the UK and Belgium have significantly more records, as shown in the graph on the right, and most of the records for the countries are concentrated between 1980 and 2020. For our pre-processing step, we begin by filtering data to a specific range from 2002 to 2021 and limiting to countries, getting rid of multiple areas and income categories that aren't relevant for our purposes. And then as we continue, we perform manual standardization of features, calculating mean and standard deviation as shown in the code.
And going on to feature engineering, our goal is to figure out what complete features we have and which ones we need to actually select for our clustering. So as you can see on the right here, we have a list of complete features right here, and then we go on to processing on the actual dataset where we select our features. So we decided on these features right here for our actual clustering task that will be used in the k-means and the k-median. And our goal, what we're looking for, is high efficiency clean energy countries or high volume mixed energy countries and developing energy systems. So if you look on the right side, we have our features that we all selected from the previous slide all laid out. Now for processing on the data set, we're splitting it up into 5-year periods: 02 to 06, 07 to 11, 2012 to 2020, 2016, and 2017 to 2021. We're doing this so that we can see the progression of countries over a 5-year span and how they're moving in the energy direction. And we're doing this to see how they correlate with our 3 clusters defined in the previous slide that we defined right here. And what we do is we import the k-means model from sklearn, and then we perform the clustering task with using n clusters, and our random state 42 ensures consistent results for every single iteration. And then here we analyze our centroids. So over here, when we actually analyze the data, we can see on the right side that we have a 3D cluster of our features from 2017 to 2021, and we only ended up getting one country cluster 2. Now on the left side, we're analyzing what the actual centroids, i.e. the means of each cluster, indicate. And when we look further, we notice that the cluster 2 indicates a country that's high in electricity generation and high in greenhouse gases. And the country that when you look further is actually China, which makes sense. Now for our k-medians implementation, we actually created our proprietary k-medians class without using sklearn. And this incorporates fit and predict methods. Fit, which uses randomization, as you can see within the code, and predict to calculate the Euclidean distances that we use in the actual task. So for processing, it's very similar to the k-means implementation, as we use the same 5-year periods, analyzing the same sort of clusters with 3 components. And the code is relatively similar, except we just implement our own created class, as you can see back here. Now for the actual results, the clusters in each period are evenly distributed within all ranges, as it is much less sensitive to outliers as compared to k-means. And there's an example of one period in clusters on the right from 2017 to 2021, with cluster 0 emphasizing fossil fuel usage, high carbon intensity, and lower renewable energy shares. Cluster 1, which represents moderate fossil fuel and renewable energy mix, and cluster 2 highlighting renewable energy, low carbon intensity, and lower greenhouse gas emissions, using all of these centroids as shown here with the corresponding features. Now for comparison analysis, we use similar code to the processing stage in order to display side-by-side metrics, 3D plots, and bar charts as shown above.
And as we continue to the next page, we can see that k-means is much more balanced in terms of clustering, more even distribution, unlike k-means with more, which has much more extreme cases, such as a single cluster having 10 or less countries. And we can also see that k-means is also far less sensitive to outliers, which all leads us to our final recommendation of k-medians. Thank you for listening to our presentation, and we hope you enjoyed.
Have a great one.